Thanks, Dr. Kadri. Well, thanks for having me. I actually submit a little more verbose title, but they probably wisely cut it down to something more pithy. But what I'm going to talk about really is where I think we're headed for the future of managing complex disease, and in particular how technology is forging a closer interface between biology and clinical medicine that hopefully will provide a much bigger impact into how we make clinical decisions and manage our patients. So as mentioned, I am in Buffalo. I chair the Department of Dermatology there, but in Buffalo is, let's see if we're, I work in this beautiful building here. There's actually a lot going on in Buffalo at the medical campus. There's five or six new buildings under construction right now, so it's an exciting time to be there. But actually, I am Canadian. I grew up, however, in Edmonton, Western Canada, so I'm still a big Oilers fan. And I know you guys might be mad that we keep winning the draft lottery, but I think you guys are okay with Austin Matthews as well. So we can think of disease very broadly as either a single factor issue or a complex disease. And single factor disease, as stated, would be that there's a clearly defined etiologic factor. Whereas complex disease, there are multiple etiologic factors at play. And so I have one interactive question, and which of these of the following is not classified as a complex disease? Skin cancer, hypertension, a fracture of the tibia, or lupus? Right, everybody's got it. So, of course, there are a number of diseases where, say, there's an infection, a UTI or something, a broken bone, and certain genetic inherited diseases like cystic fibrosis or sickle cell disease where there's a single gene. And in general, medicine has been pretty good at identifying these etiologic factors and in some cases in providing good cures for them. But most disease burden is complex. And the three most relevant and prevalent disease burdens in our society are cardiovascular disease, cancer, and autoimmunity are neck and neck. And so because I'm an immunologist, I'm going to focus the discussion on autoimmunity, which is, of course, the failure of an organism to recognize its own constituent parts as self, which results in immune response to its own cells and tissues, or horror autotoxicus, as Paul Ehrlich had coined. There are over 100 human autoimmune diseases, and they affect 5 to 10% of the population. Maybe up to 20% of the population has some autoimmune phenomenon. And autoimmunity then is the second or third leading cause of morbidity and mortality. And of course, it is a complex disease with complex etiology. That means it's multifactorial. There are both genes and genetic and environmental factors that conspire together to cause an immune dysregulation and cause disease. The problem is we don't know most of what these genetic or environmental elements are and exactly how the immune system is dysregulated. And complicating matters further is that there are two sources of complexity in human disease. So there's the biological complexity, where the genetic environmental factors and our response to environmental exposures and how they intersect and interact with each other. But on top of that, there's a clinical complexity. So disease is not just disease. There are many subphenotypes, many flavors, much variability in disease expression. So there's this disease heterogeneity as well that we have to deal with. So right now, where are we at in 2016? We really can't identify individuals at risk very well. We can't predict the extent or course of disease. And we do a poor job of matching treatment to expected responders. We hope sometime in the future that we'll be able to apply a real scientific rationale to clinical decision making. So our goal ultimately is to determine the comprehensive set of factors and interactions between these factors that impact disease risk, diagnosis, disease prognosis, and treatment outcomes. The challenge is to deal with the biological complexity in the context of clinical complexity or disease heterogeneity. So the strategy that some are undertaking is to leverage emerging technologies in terms of genomic, genetic, and proteomic technologies to generate and integrate large-scale clinical and biological data. And because I'm a dermatologist, I'm going to illustrate this by some of the work that we're doing in a disease called pemphigus vulgaris, which is a life-threatening autoimmune skin blistering disease. Blisters in the mouth and the body, very nasty, and can still, I had 2 patients die with it this year. So what we're doing is to deconstruct disease complexity. What we're doing is constructing biological profiles by looking at the genetics and immunological details and trying to address environmental exposures as well to find out what is really, at the granular level, at the biological level, what is really going on in terms of all these biological elements in patients with disease, and then link this information to the clinical profile of patients that have been subphenotyped based on a number of parameters that are either static or dynamic. So gender, your age of onset, are you in active phase of disease or in remission, what type of lesions you have, just in the mucosa or mucocutaneous, and so forth. So to do this, we've been working at multiple levels. So we've been working at the DNA level. We HLA type every patient that comes in. We've just completed a big whole exome sequencing project that has revealed some exciting stuff that we hope to submit very shortly to a leading journal. We've been doing a lot of gene expression profiling at the RNA level to look at transcriptional dysregulation in patients, in subgroups of patients. And at the protein level, we've been doing more array stuff, multiplexed cytokine beat arrays, multiplex autoantigen arrays that we produced ourselves in the lab, where we can collect a lot of data in a much more multiplexed and robust way than we could in the past. And we're able to do this because we, over the years, have collected enrolled a lot of patients into our translational studies, and have one of the largest collections of patient samples and clinical information in the world. Now, this is a rare disease, so these numbers are relatively small, but they're huge for this type of rare disease. And what we're doing is taking that information from all those different levels that I talked about, from DNA, RNA, and protein work and immunological subsetting, and integrating this, creating a biological profile of what is going wrong in disease, and integrating this in a matrix fashion with the clinical profile, so depending on what type of subphenotype a patient falls under. And ultimately, so I call this a disease array, or an informational array, a virtual array, that will help us deconstruct the complexity of disease. And ultimately, what our goal is, and we're starting to work with some systems biology people, is to take this information, integrate it, and come up with actually a quantitative measure, a disease factor that might tell you numerically your chance for this diagnosis, your chance for a certain prognosis, or treatment outcome. And ultimately, where I see this headed is that we want to take this information, and you might be able to map this in a 3D fashion that was actually published earlier this year in Science in the cancer world, where they have this cancer immunogram, meaning you take this information and the computer spits out where you might fall in this 3D map. It's sort of a radar or a heat map of your likelihood for diagnosis, or a certain prognosis, or response to treatment. So what we're doing is taking the biological profile, linking it to the clinical profile, putting it in, trying to develop an informational array or factor or 3D plot that would allow us ultimately to take unstructured data into structured data and inform our understanding of disease processes, and ultimately come up with clinical applications in terms of biomarkers to guide our decision making, and more targeted, specific, and individualized treatment. And the inputs for the biological profile and clinical profile are only going to increase, and I think particularly as we rely on sensors and point-of-care information to get us more biological information, and more real-time and mobile input for the clinical information, we'll have more information to continue to iterate and get more further down this pathway. So technology really is then driving, I think, an increased interface between biology and medicine, where we're developing quantitative tools to filter complexity into accessible units of comprehension and utility, to model disease outcomes and reach that holy grail of precision and personalized medicine. And in order to do this, I think we are going to have to embrace and rely on some paradigm shifts. I think we really miss an opportunity every time we see a patient in the clinic. We should be collecting data and biological information and samples on pretty much every patient that we see in the clinic. Big data is going to, as mentioned, is going to be the new drug. We've got to go from what do we think to what do we know. And ultimately, we have to increase not just on the educational front, not just the way we teach our physicians, but also the public at large, so patients have a better understanding and can be participatory in their care. So when are we going to reach this, where we have a more scientific rationale to clinical decision-making? Well, that's hard to predict, but I like the quote by the computer scientist Alan Kay: "The best way to predict the future is to invent it." And I think with continued partnership with academia and industry, we'll start to build this future. So thank you very much.